Sticking the hydrogen atom to the oxygen atom is a covalent bond. Okay? Covalent bonds are strong. That's why when you boil water, there's not enough energy to break those bonds. So it does not split up into hydrogen and oxygen. It stays together as a water molecule. Too strong to break when bonding, when boiling. However, we have these other forces, these intermolecular forces, and I'm going to draw that down here. If we have a water, I don't know if you remember, but the oxygen part is somewhat negative, and the hydrogens are somewhat positive. So what's going to happen is if you have one water molecule and a second water molecule that line up like this, and I'm going to start using the abbreviation for molecule, because molecule is a big, long word, and we use it a lot. I'm going to start writing capital M, capital C. Okay, so if you want to use that to abbreviate for molecule, you can. So we have one water molecule, we have a second water molecule. What do positive and negative do to one another? They attract. Positive and negative attract. Now, does anyone know what the prefix inter means? Between. Inter means between. So if you go on an international flight, you are traveling between two different nations. So what we have here is we have a force. This is a force between molecules. If inter means between, and we are between molecules, what kind of force could we call that? Intermolecular force. Okay, so those are an intermolecular force. I've not really left myself enough room here, so I'm going to have to throw that up there. So this is an intermolecular force. And intermolecular forces they're not strong like those bonds within the molecule. They are weak. So when you boil the water, let's say that this is my water molecule here. Okay, and what did I do with my other magnet? Where'd you go? No. Oh, there it is. Okay. So let's say that this is one water molecule and this is another water molecule. I know they look different, but unfortunately, my other ones like this don't work properly with each other. Okay. Now, if this is a water molecule, this end is a hydrogen, this end is a hydrogen, and this would be an oxygen, yes? Is it easy for me to break this apart? No, and that's because they have strong bonds. But if this were another water molecule, I know you're going to have to use your imagination here. What do? They attract. However, what can I do? I can separate them because this force is much weaker than the force that holds the top of this thing to the bottom of this thing, right? I would have to do some pretty serious sawing or something to get this broken apart. But this one I can just take apart. So when things boil, there's enough energy to break the intermolecular forces, but there's not enough energy to break the bonds and break the water molecule apart. Okay? So when water boils or evaporates, the molecules, these are what break when water boils. All right. So I wanted to just go to page 52 really quickly, and let's take a look at number 4. Which picture is correct? If this is boiling, A is correct because we break the intermolecular forces. Now, which of these represents a physical change and which one represents a chemical change? Which one is physical and which one is chemical? A is physical because the particles stay the same. And what would B be? B would be chemical. And in a chemical change, you start with different particles and you finish with different particles. The atoms rearrange themselves. Is good? Okay. So today we're going to focus on some chemical properties, chemical changes, and then tomorrow, if I can get my act together, we will do a little lab about some chemical properties. Okay? So I think that would be a nice thing to do just before our long weekend. Okay? So let's pop to page 53. Now, I don't know if you've heard the word property before. Have you heard the word property? Yes? What is a property? If I said, what is a property of this clip? You could say the clip is blue. That is a property of this clip. What else could I say about this clip? This clip is also magnetic. Yes. Oh, look, I can make it move. That's kind of fun. Is this clip soluble in water? No. So that's another property. What state is this clip? It's solid. So that would be another property of this clip. If I were to heat this really high, do you think it would burn? Hard to say. We would actually have to test that, yes? And we're not going to test that because I need to use my clip, okay? But we will test magnesium ribbon and we'll see if it's flammable, okay? So a property is a characteristic of a substance. You can use a property to describe a substance. All of the properties that we described about this blue clip, do you think those are chemical properties or physical properties? They are physical properties. In order for something to be a chemical property, we have to say, how does it react? Yes? If I were to put this in acid and it dissolved in acid, that would be because it's reacting with the acid. That would be a chemical property. So usually when we're observing things, we're mostly observing physical properties. Because physical properties are just things you can observe. A chemical property, you either have to heat it to see if it'll burn, or you have to mix it with another chemical to see if it will react. So chemical properties tell you how a substance reacts. All right, whereas physical properties, you observe it without changing the identity of the substance. So you can say, what temperature does water boil at? That's a property. That's a physical property because you're still keeping it water. If you are looking at a chemical property, that's going to be when it changes into a new substance. So what I'd like you to do is I would like you to go through this list and decide which of these are chemical properties and which are physical properties. And then once you get through 1 through 14, if there are any words from here, maybe like flammability and solubility, malleability, ductility, you're going to list those words down below, okay, with the definition. If you already knew them, you don't need to write them, okay? You're chemical or physical, list any words that are new to you with their definition. Yeah.
Matter will be charged to do something that will work. You burn a mushroom. It's a mushroom. It is a mushroom. But it's liquid. It's small in mushroom. It's scientifically, how's it going? It's more than people solid. You really solid.
Thank you.
Genuinely and seeing very well. That means you can be, you know what I have going.
It's just a crystal and how it's put together.
I didn't know before.
Okay, I think most people are getting close to finished. So I'm going to interrupt you for a minute and we're going to turn to page 54. On the previous page, we talked about chemical properties. And physical properties. But on page 54, we're talking about physical change and chemical change. Okay? A physical change is just when you're looking at something and you're like, oh, well, if I were to take the water in here and freeze it, that would be a physical change. Yes? If I took this water and I threw some sodium metal in, which would be kind of exciting, that would be a chemical change. Okay? So just a reminder, our states of matter, solid, liquid, gas, and what's the fourth one? Aqueous, meaning dissolved in water. Physical change, you have no new substance. It's a change in size or shape or state. And it includes dissolving, which I know is written there, but I want it to be big. Dissolving is physical. What would happen to a dish of salt water if you left it out overnight? Or maybe out for a week? You would get salt crystals, right? Because the water would evaporate. So dissolving is physical. Recrystallization is also physical. I feel like there's only one L in recrystallization.
There's two.
Are there two? Okay, it just looks weird in capital letters. Anyway, yeah, there it looks right in lowercase, but it looks weird in capital. All right. Tell your partner, while we're here, what do we call it when we change from solid to gas? Solid to gas is sublimation. What do we call gas to solid? Deposition. What do we call gas to liquid? Condensation. And what do we call liquid to gas? Evaporation or vaporization. Okay? So those are all physical changes. A chemical change is where a new substance is formed. In a chemical change, the atoms rearrange. That's the key thing, is that the atoms rearrange into new and different substances. So what I want you to do now is I want you to think about each of these things and think to yourself, do we get a new substance? If we get a new substance, it is chemical. If there is no new substance, it is physical. Go ahead and try those.
You're meant to be the smart one.
Pardon me? Tarnish? Yes. To tarnish means, like, if you have a metal, it sort of gets like a haze on it, like it goes black or something like that. So if you've got silver, it turns like black, yucky. Yeah, except for not rust, because rust is like specific for iron, but any kind of metal that sort of gets like a layer of stuff on it. Yeah?
Whoa. I had to write it out.
Okay, let's go over these really quickly. Shh. Table salt dissolves in water, chemical or physical? Physical, because dissolving is physical. What does it mean to say that silver tarnishes? It means you get like a layer of like a different color on it, okay? Rusting is a type of tarnishing, but if you get silver, like silver, silverware or whatever, people used to have to polish it all the time when they used it because it would get a layer of a silver oxide on the top. Chemical or physical? Chemical. An apple is cut. Physical. Heat changes water to steam. Physical. Baking soda reacts to vinegar. Chemical. How many people have mixed vinegar and baking soda? Anyone not mixed vinegar and baking soda? Go try it at home. Just make sure you do it in like a sink or something. Okay? It's a little bit exciting. Little chemistry at home. Iron rusts. Chemical, because we end up with that rusty, the brown, flaky stuff. Alcohol evaporates. Physical. That's a change of state. Ice melts. Physical. Ooh, I need to fix that. Fix vinegar. Okay, there. Vinegar. Milk sours. Chemical. Sugar dissolves in water. Physical. Wood rots. Chemical. Pancakes cook. Chemical, because you start with this wet batter, right? And as you cook it, it solidifies, right? So that wouldn't be happening if we didn't have new bonds forming, okay? Grass grows. Chemical, because what happens is grass lots of grass is made up of little sugars, and sugars are hexagonal shaped. I'm not showing this very well. This is not what it looks like at all, but we're just gonna draw it like that. Where do these little sugars come from? Does anybody know? How does the grass make its sugar? Yeah. From sunlight. So we have the sun. Ooh, photosynthesis. Yes. Does anyone know what you need in addition to sunlight? Yes. You need carbon dioxide, CO2, carbon di means two. Yes. You need, no, you actually don't. Not nitrogen. Now, when we burn sugar, right? That's how we get our energy. We burn sugar. What comes out as a waste product? What's produced by our body? When we breathe out, we breathe out carbon dioxide. Okay, so there's the carbon dioxide. If you breathe onto a mirror, what happens? So there's also water. So what the photosynthesis does is it takes carbon dioxide and water and it turns it into, this is a simplified sugar, C6H12O6. And we would need 6 carbon dioxides to get the 6 carbons. We would need, this requires a little bit of balancing. We would need 6 of these. And our other product is O2. So the plants actually make the oxygen. 12 plus 6 is 18. 6. There we go. Okay? You are not responsible for knowing that, but what you can see is that all that carbon dioxide in the atmosphere, the water that the plant sucks up from, the ground or that absorbs through its leaves, it's turning that into sugar. And it's rearranging those atoms. It used to be a single carbon with 2 oxygens, and now we have 6 carbons, each stuck in a little ring. You can imagine each of these little corners is a carbon, and they bond together and they make the structure for the grass. So that's why grass growing is a chemical process, because in order to get bigger, you need to build those sugars and various other chemicals that make the grass blade itself. Okay? Like I said, you don't need to know the details of it, but you should know that it's a chemical change. A tire is inflated. That is physical. Food is digested. Chemical, unless you want to talk about the stuff that happens in your mouth, because when you chew it, that is physical. Although there are actually enzymes in your mouth. One's called salivary amylase, and it breaks down sugars. It breaks down starch into sugars. Paper towel absorbs water. That is physical. Okay, very good. All right. I don't like this diagram. This diagram irritates me. So we're just going to skip it, okay? The only thing I'm going to point out, actually, if you are interested on this page, intensive properties do not depend on the amount. Extensive properties do depend on the amount. So this is on page 55. So let's think of things that do not depend on how much there is. Color. If I broke off a piece of this clip, would it still be blue? Yeah. Yes. Taste. Does it taste the same? Does it taste the same if I had a smaller piece? Yes. If I were to melt it, would it melt at a different temperature if I had a big piece or a small piece? Yeah. Not at a different temperature. If you have water, if you have ice, what temperature does ice melt at? 0 degrees Celsius. It also freezes at 0 degrees Celsius. Does it matter if you have a whole lake full of water? Does that temperature change? No, it's still 0. Even if you just have one ice cube, it's going to melt at 0 degrees. If you have a whole lake that's frozen, it's going to melt at 0 degrees. Okay, so it doesn't matter how much. Whether it's soluble, whether it's ductile, whether it's hard or malleable, whether it conducts electricity, all of those do not depend on the amount. So all of those things are called intensive properties. An extensive property depends on the amount. So it's usually something that you're measuring, like mass. If I broke off a piece of this clip, would it have a different mass? Yes. If I broke off a piece of this, would it have a different volume? Yes. If I broke off a piece, would it have a different shape? Yes. Would it have a different length? Yes. Okay, those are extensive properties, and they depend on the amount. But those are enriched words. If you don't care about them, you do not need to learn them. Okay? So you get to go through now page 56 and 57. And then let's just take a quick look at page 58 because I want to go over this with you. This is page 58. So we are going to, on this page, classify each of the following as chemical or physical. Now, if it is chemical, remember, the bonds change. You get a new substance. So take a look at A. Does A look like a chemical change or a physical change? Have we got a new substance at the end? Or is it the same as before? Okay. Here's the substance in the first beaker. I've got some paper clips. Here's the substance in the second beaker. I have some binder clips. Now I have some paper clips mixed with binder clips. Do I have a new substance? No. So is that chemical or is it physical? This is physical. And then I get to decide if it's physical, is it melting? Is it freezing? Is it evaporating? Is it condensing? Is it sublimation, deposition? Is it mixing or is it separating? Which one just happened here? Did we have a change of state or did we have mixing or separating? This was mixing. Let's do B. Does this look like a chemical change or a physical change? Discuss with your partner.
Yeah.
Chemical change or physical change? Chemical, because we have new bonds, new particles. We used to just have our old particles, which were separate. Yeah? And now we have the new particle, which is together. That means this is a chemical change. And if it's a chemical change, you don't have to go any further because it's just chemical. Okay? Do you think you could do the rest of them? Yes? Okay, so why don't you start with pages 58 and 59 and 60. And if you finish those, you can go back and do 56, 57.
Yeah.
Ah, exactly.
Oh, it's. I've seen it. Are you then just kind of like.
I'm gonna put 58 to 60 as the homework, but I'll probably add the other ones because I think we'll have time to finish it mostly in class today. Okay? See how far you can get. I'll see if I add that on.
Oh, it's the opposite of.
Mixing or separated. Well, this one goes back to part of and now the black ones are separated. What mixing, reduce chemical sign that.
So you can use the what size?
That one looks like.
Yeah, what
It looks
size?
like. Water. What did it say that?
Which one
Yeah.
is F? Is it those?
Let's take a look. I would say F is and it is mixing. So it would be like salt crystal dissolving in water. Yeah. Yeah.
I feel like I'm not Chinese.
So, yeah, that's, yeah.
With most things.
Okay, so. And then. This one goes. That's or supply. Thanks.
But all except for being. Actually. Right, yeah.
Oh, we don't, this guy. One
I wrote dissolving. I guess it's getting
Mixing that.
a mixture of the black.
No, because it's so is the water.
Yeah, well, it's anything is like. No, physical. How many what's it called? The head looks a bit long. Sorry.
So that was.
Yeah, I don't understand these words.
Liquid gas, no, it's H2O gas, the H2O gas, so it's, deposition.
Wait, so for that one, the they, that one.
For that one, the gas.
This
So
one.
it's radio gas.
That's right.
Deposition.
So each one has different. Updated.
Yeah, yeah, so this one, I mean, they'll both be physical. First direction, if you go from solid to gas. No change. Yes. So it changes. Oh, yeah. Okay, yeah.
Oh, yeah. Oh, that's what I did. It's still kind of small.
This one is chemical.
These ones are just.
You might have read a word. Don't you yeah.
Argon is not reactive, that's chemical, because this doesn't react. So you can try and catch it on fire, and that tells you how
Physical or chemical?
And it doesn't, it's not flammable, so maybe.
Describe it. Describe it. Exactly what I'm about.
It's either that or.
So the shadow. Look at it.
It's not like you're right, so if I have, yeah, no, here's the difference, right?
It's just.
Where do you bring out the boat? What did
How are you?
Kiwi help.
Yeah.
Look, so what she said, the main point is, look at this bond, it's black. Black is the bond here, it's white.
It's not in a station.
That means the bond change.
Yeah, I'm gonna make all of 57, 56 to 60 should be done, okay?
Okay. Strength. Look at it now. Cross. So it changed. So the bond changed. So easy. So get the bond. Yeah, so it's for a chemical change. Well, it's a solid.
Yeah.
So it's
And all it looks like we're yeah. This would probably be like well you pretty comfortable, right? Yeah, it's probably solid. You're going down.
I've seen even.
Oh,
they made it water.
If it's moldy. What? Moldy red. Evaporated the water. So if there's no, if there's no main charge.
What is this? That's another way. I'm gonna. So very right.
You imagine the more water. Right? But if you have ice cream.
Oh, you got friendly fire. Like it's shaped.
Imagine, yes, we put water. Yeah. Okay, what's the gas? Gas. You don't have.
Girl, I saw them. I thought that was a normal video. You were there when I first came out. Did I sleep? Down here. It's to grab so much. Yeah.
Well, whereas extensive, like.
I didn't really try.
But you don't know when you do.
You asked that. First of all, you did this when I get. Oh. Huh?
Yeah, wrong. I might be doing it.